Welcome back to the deep dive. Today we are strapping in for a very specific journey into the world of functional programming.
And we're tackling a language that, let's be honest, can feel like a beautiful but sometimes tricky mathematical puzzle box.
That's right, we're talking about Haskell. Our focus today is on the absolute fundamentals, the structure of a basic Haskell application. We're going to be analyzing the code in appmain.hs and acreoclib.hs.
And the mission here for you is to get beyond just reading the syntax.
Exactly. We want to understand the profound meaning behind every compact line, especially when it comes to, module contracts, and this is the big one, white space.
That mission is so crucial because in Haskell, the philosophy is baked right into the syntax. Structure and function are just so tightly linked.
So if you're coming from, say, an object-oriented background, some of the rules can feel
Almost counterintuitive. Yeah. We're using your sources to highlight how Haskell uses this explicit modularity, defines its public APIs with startling clarity, and yes, enforces actual laws around indentation that define the scope of your entire program.
Okay, let's unpack this then, starting right at the application's front door.
The very beginning.
We look at the very first line of appmain.hs, which is module main, where. Now, we know main is the required entry point. It's where execution begins.
Right.
But if you're used to seeing parentheses for, argument lists in Python or C, that little bit, main, it looks suspicious. It's not an argument list, is it?
It is absolutely not. And what's fascinating here is that the source material points to this exact element as a classic trip hazard for newcomers.
Okay.
In this specific context, the parenthesis around main is explicitly an export list.
No, export list. So it's not defining what the module receives, but what it offers to the rest of the world.
Precisely. It's the public API for the main module. This is really the cornerstone of Haskell's strong encapsulation.
So it's telling the compiler.
Telling the compiler, hey, I might define a dozen helper functions or data types inside this file, but the only thing available for external use or compilation linkage is this one function, main.
Wow. So it's an explicit definition of the module's interface, hiding everything that isn't essential.
It is. The clarity of that contract is one of the language's core strengths.
That's a great insight into the structural philosophy right there. It forces you to think about what is private and what is public from literally line one.
Exactly. If you define 10 internal functions in this file but forgot to list them there, in that export list,
That may be inaccessible.
just inaccessible. It enhances code security and modularity by default.
And the where keyword.
The where keyword simply acts as a clear marker. It just signifies the end of the module header and the beginning of the module's body. Simple as that.
Okay, so with the entry point defined, let's see how these modules actually communicate. We see that contract in action on line 3, import lib.
And that's the call for external resources.
Okay.
That line pulls in the library module, which, following the application structure in the source, lives in circlib.hs. And we can infer from the successful import that the lib module itself must have its own similarly explicit export list. Something like module lib, some func, where
It's like a handshake. Lib says, I offer some func, and main accepts it.
it's a perfect handshake. It means main only gets access to what lib explicitly put in its parentheses.
Yeah.
If lib had other internal functions not listed, main couldn't touch them.
So Haskell's entire core architecture is built on these explicit declared contracts, what you expose and what you consume.
All driven by those critical parentheses in the module declaration.
Okay, now this moves us to the structural question that I think really distinguishes Haskell from most mainstream languages. We established that the body of the main module begins after where, but then the source material forces us to ask, how does the compiler know when the module body ends?
Right. Where's the boundary?
Exactly. If we look at, say, Elixir or Ruby, they use do.end. If we look at C, Java, or JavaScript, they rely on curly braces. What is the syntactic boundary here?
This is where we hit the absolute aha moment for anyone transitioning into this ecosystem. This missing boundary is solved by something called the offside rule.
The offside rule.
Yes. And for you listening, understand this. In Haskell, indentation is not a style preference.
It's not just for readability.
No. It is a syntactic law. It dictates scope where other languages use explicit delimiters. It essentially replaces the need for open and closing braces.
Indentation is law. That's a huge mental shift. I remember the pain of training myself to respect Python's indentation, but this feels even more rigorous. Why did the designers choose this path?
Well, it really stems from a philosophical trade-off. They traded the visual clutter of explicit markers like braces and semicolons for the strict discipline of indentation.
And the argument is what? That it's just cleaner.
The argument is that well-indented code is inherently easier to read, and by enforcing it as law, they ensure consistency across every Haskell codebase ever written. It simplifies the syntax, but it demands strict adherence from the programmer.
So let's discuss the convention versus the rule here. The source emphasizes that top-level declarations, imports, functions, data types, they typically start at column 0. Is that part of the rule itself?
That is a key distinction. Column 0 is a deep-seated community convention.
A convention, not a rule.
Right. It's a habit that helps programmers visually separate things that are, global to the module from local blocks of code that have their own smaller scope. The offside rule itself deals with how new blocks of code are open and closed by comparing the indentation of subsequent lines.
Okay, so let's look at a concrete local block where the rule is strictly enforced. We often see the main function implemented using a do block, like the one in the source.
Yes, the example was something like main.do, and then on new lines, indented sumfunc, and put strlen hello world.
Right.
In that structure, main su starts an IO sequence. That do keyword establishes the margin. The lines that follow sumfunc and put strlen, they must be indented relative to that do keyword.
And if they aren't?
The compiler checks the column of the first line after do, and every subsequent line in that block must start at the same column or further to the right. The moment a line of code returns to a column that's less indented than where that block started.
The compiler assumes the block is finished.
Exactly, the block is closed.
That clarity means that if I accidentally tried to define a completely separate function right after the do block, but I kept it indented,
The compiler would likely treat it as part of the do sequence, and your program would just break down. The discipline is total.
it is. And for those listeners maybe tempted by familiar syntax, we have to highlight the escape hatch.
Yes, the source does note that Haskell does technically support C-style explicit braces and semicolons.
The ultimate unidiomatic move.
Precisely. The community provides this massive collective warning. While the syntax is technically valid and lets you ignore the offside rule, using it is incredibly rare.
It just flags your code.
It instantly flags your code as unidiomatic. It's a fascinating insight into the culture. Flexibility exists, but consistency is valued so highly that violating the convention becomes a kind of, a social technical breach.
They just prefer the clean, predictable appearance.
Exactly. Enforced by the offside rule.
That tells us a lot about the philosophical priorities of the language. Its simplicity of appearance and consistency trumping the freedom of the individual programmer.
Its structure is a social contract.
Okay, that covers the layout. Let's shift from the overall structure to the actual function definition details, focusing on the type declaration on line 5, main.io. This is where the functional jargon really comes to life.
Indeed. Let's break down the type signature itself. The syntax is the easy part. It's just read as has the type of
a type declaration.
an explicit type declaration. It's a non-negotiable requirement for critical functions in a statically typed language like Haskell. The compiler knows exactly what this function is designed to take and what it is guaranteed to return.
So the main function has the type of IO. Let's start with IO.
IO stands for input-output. In Haskell, this type is the famous IO fence. It indicates that the main function is an IO action.
Meaning it performs side effects.
Exactly. Side effects. These are actions that interact with the external world.
Yeah.
Printing to the console, reading files, getting user input, sending network packets, all that messy stuff.
Wait, but if Haskell is a pure functional language, aiming for that mathematical purity where functions always return the same output for the same input, what does that IO fence actually buy us?
That's the key insight. The IO type exists to explicitly quarantine those impure actions. It creates a formal separation.
It cordons them off.
Perfectly put. By marking main as IO, the compiler knows that any function not marked IO is guaranteed to be pure. That means it has referential transparency. It's a mathematical function that won't surprise you.
So the IO marker means, okay, this section talks to the messy, unpredictable real world, but we've cordoned it off so the rest of the application can operate with guaranteed purity.
Exactly right.
That elevates the concept way beyond just saying it has side effects. It's a guarantee of purity for the rest of the code base. That's neat.
It's a very powerful concept.
Now, the final piece, the parenthesis, that's the return value, right?
That is the unit type. And while you might relate it easily to, say, none in Python or void in C, representing the absence of a meaningful return value in Haskell, the unit type is actually essential.
Essential because of type theory requirement.
Exactly. Why is it essential? Why can't it just be implicitly void? Because in Haskell, every expression must have a value and a type. Every single one.
Okay.
So even when a function's primary purpose is just performing an action, the I/O part, it still needs to return something of a valid type to satisfy the compiler and the type system.
So the unit type is just a placeholder.
It provides a placeholder value that signifies completion or success without carrying any meaningful data. It's a value that takes up no space beyond its type definition, ensuring this strict rule, everything is an expression, remains true.
So the full declaration, main IO, is a highly specific, very disciplined way of telling the system. This is a carefully managed action that interacts with the real world, and once it's done, it yields a placeholder value just to confirm completion.
You got it. That makes the abstract concrete.
And that ties us into the final line we're analyzing here, which is just main sumfunc.
And since sumfunc itself is defined to be an I/O action in the imported lib module, this final line simply wires the entry point directly into that core logic. The structure is complete.
Define the contrast.
Isolate the impurity and execute the primary action.
Fantastic. We started this deep dive looking at a deceptively simple Haskell file, and we've uncovered explicit module contracts, a social agreement enforced by the offside rule, and a philosophical guarantee of purity secured by the IO type.
It's a lot packed into just a few lines of code.
It really is. So to quickly summarize the most important takeaways for you, Haskell's architecture uses explicit module declarations for structure and demands an export list, those critical parentheses, to define its public API. The language fundamentally relies on the offside rule, making indentation law. It trades explicit braces for strict discipline to ensure universal code consistency.
Right.
And finally, the core function, main.io, is this clear type signature that acts as the IO fence. It quarantines side effects while using the placeholder unit type to satisfy the requirement that every expression must yield a value.
And this emphasis on strict rules and convention brings us back to the biggest philosophical point. The Haskell community's preference for the rigid structure of the offside rule and explicit types over, the flexibility offered by optional braces is profound.
So if the language's syntax is designed to be mathematically consistent and guaranteed for purity,
how does this inherent rigidity influence the thought process of a programmer learning it? And what does this demand for structural consistency tell us about the priority of maintainability and architectural integrity in complex software design?
it's a fundamental question.
It is. It's about how the structure of a language shapes the very quality of the code we write.
That's a powerful thought to leave you with. Does the structure we choose define the limits of our solution? Thank you for joining us for the deep dive.